Now for something somewhat different, linearizations and differentials. So let's wrap up chapter 3. This is, though the conversation's a little bit different, this is basically the same stuff we've been doing, which is approximating a function with a line. So the plan is, in this section, to approximate functions locally with functions whose graphs are lines. So we've been finding the equation of a line tangent to a function for several sections now. So this is just a slightly different take on that. These linearizations are based on tangent lines to the function. So for differentiable functions, we'll be doing quite similar type things as we've done in the past, though the conversation will verbally be a little bit different. We'll finally give a proof of the chain rule. I still owe you a proof of the chain rule from several sections back, and we'll go through with some epsilons and some deltas, well, some epsilons at least, and some limits, and establish the chain rule formally. Okay. Next definition is the same thing we've been doing, only the notation's different and the verbiage is different. If f is differentiable at x equals a, then the approximating function L of x equals f of a plus f prime of a times x minus a is the linearization of f at a. The approximation, f of x, this little wiggly equal signs means approximately equal to, f of x is approximately equal to L of x. Approximation of f by L is called a standard approximation of f at a, and the point A is called the center of the approximation. All L of x is the line tangent to the graph of y equals f of x at x equals a, written in terms of a function. Instead of y equals mx plus b, which is what this is, were we to rearrange it, it's written as L of x. So it's a new function. It's in the verbiage of our calculus book, a linear function, because its graph is a line. Beware, that's not the standard use of the term linear in most other settings. But the picture is exactly this. So we've simply taken a function, a differentiable function at x equals a, and we've found the equation of the line tangent to that function at x equals a, and described it as itself a function, L of x. So L of x is a good approximation of f of x when x is close to a. Okay, now we're not going to put a clean meaning on what that means, what close to is exactly. We're going to look at pictures and play with numbers in this one. So this is a bit more informal section, really. Here's how L of x approximates f near a. First off, if I plug a into L of x, then it precisely matches the function. At a, L of x and f of x are the same. They both produce this point. As you can see from the definition, if we'll plug in a for x, we'll get L of a equals f of a plus, plus 0, because this part will be 0 at x equals a. So the L function equals the f function, the linearization, equals the function itself at x equals a. We're going to think of this approximating in a different way. Also, the linearization has the same derivative at x equals a, as does the function y equals f of x. That is, L prime of a equals f prime of a. If you differentiate L with respect to x, L prime of a would be f prime of a, the coefficient of x, the slope of the line. So think in terms of approximating in this sense. L of x takes on the same value as f of x does at x equals a, and L of x has the same derivative that f has at x equals a. How about second derivatives? Does L of x have the same second derivative that f has at x equals a? In general, no. In the picture, no. But in the future, this is future, calculus 2 future, we might go through and try to approximate functions at points by matching up the value, the first derivative, the second derivative, the third derivative, and so forth at a particular point x equals a. When you do power series in the future, you'll see it addressed in that sense. But for now, hey, L of x is just the equation of the line tangent to the function f of x at x equals a, written as a function itself, L of x. So linearizations are tangent lines, so we should be pretty good to go in computing linearizations. It's just a matter of computing derivatives and manipulating them appropriately. The book, I'm laying this on the book, they seem to make a big deal out of the following. They repeatedly push the idea that if we magnify our view of the graph of y equals f of x near the point a f of a, then the graph of the linearization approximates the graph of the function. There's several figures in this section related to that. Here's a couple of them. Here, on the left, figure 3.53, we've got a graph of f of x equals square root of 1 plus x. Square root of 1 plus x, it's a semi-parabola with horizontal axis. And what they're going to do is approximate this function, f of x equals square root of 1 plus x, at a equals 0. Okay, the semi-parabola, the function f passes through the point 0, 1. The linearization will also pass through that point 0, 1. The slope of a tangent line to, say, f of x equals square root of 1 plus x, the slope at x equals 0, a equals x equals 0, I bet you is a half. It's explained in detail in example 1 from this section. So we'll get a linearization that takes on the value 1 and has the same slope as a slope of a half. So what we get when we approximate, and granted in Theorem 3.53, they've done a linearization at 0, this line, and also at 3, this other line here. It looks like over here at x equals 3, or a equals 3, the approximation's better. Well, that's because the curve is kind of flatter over there than it is over here. It's more curvy over here. How good the approximation is going to somehow be related to how curvy the function is. But even over here where the function's curvy, if we'll take this little box here and magnify it, we'll get a picture that looks like this. So the function itself is in blue, so you can see it just barely, and the linearization is in red. And they're awfully close to each other when we magnify it. So they've increased the magnification to where these are tenths of units as labeled along the horizontal and vertical sides of the box there. So the big point is, if I were to choose, say, input values close to 0, we would get from the linearization output values close to the function values. You go far away and all bets are off. And we're not going to elaborate on precisely what close to means and how accurate these approximations are. But the idea is the linearization closely approximates the function if we plug in values close to point A, the center of the linearization. Let's do an example. Let's look at exercise 3.8.2 in the supplements, where they simply ask us to find the linearization L of x of f of x equals the square root of x squared plus 9 at a equals -4. Okay. How about we write f of x as x squared plus 9 to the 1/2, change the square root for a 1/2 so it's easier to use the chain rule. Then chain rule says the derivative is bring the exponent down, rewrite the inner function, subtract 1 from the exponent. 1/2 minus 1 is -1/2. Chain rule, multiply by the derivative of the stuff inside. That'd be 2x plus 0, if you like. You want to simplify? Yeah, probably, because we're going to do something with the derivative. The 2 and the 1/2, those cancel to leave us with x. This is negative, so it goes to the denominator, x divided by the square root of x squared plus 9. So there's a derivative for the linearization. We need f of a and f prime of a. F of a is -4, plug -4 into the original function, gives us a square root of 25, which is 5, square root, understood to mean the positive square root. F prime of a, f prime of -4, plug -4 into the derivative, into this function here, gives us -4/5. So the linearization being defined as f of a plus f prime of a times x minus a. With these numbers would be f of a was 5, a 5 goes there. F prime of a was -4/5, goes there. A itself was -4, so a -4 goes there. Simplify a little bit to get an x plus 4. And distribute and simplify. And we get the linearization as -4/5 x minus 9/5. So I bet if you'll plug in numbers close to -4 into this function, that'll give you something close to what you would get by plugging -4 into this function. Now think about it. If you're doing these by hand, it's easy to do this L of x stuff. This is just multiplication and addition. Piece of cake. If I tell you, let's take close to -4, how about -3.999? You could do the arithmetic to plug that in here, no problem. A little messy, but not too bad. But up here, you plug 3.9 or -3.999 in here. The squaring is really no big deal. It's the square root. How are you going to, by hand, calculate square root? There's techniques, and this stuff comes from somewhere. But you're not really clear on how to calculate a square root or even how to approximate a square root. The computations here are complicated. The computations here are simple. So in this linearization, one thing we're accomplishing is, if I had to do these by hand, ugly, weird computations, like taking square roots, for simple computations, multiplication and addition. We could do this for trig functions as well. If you wanted to know the value of a trig function, we're about to do an example of that. If it's not a special angle, how are you going to figure out what the value is? Well, look it up in the table. Well, that's how we did it in the bad old days. Well, where'd the table come from? Approximations. So in the broader sense, the approximation of a function with something else is done in such a way that you take a complicated function and approximate it with something you can easily deal with. We're doing that here. You'll do more of that in Calculus 2 when you see power series. So that's the big idea of approximation, is to take icky things and replace them with easy things. And we've done that. You don't know by hand how to, neither do I, how to calculate these square roots. I mean, people do know out there, but it's a complicated procedure. This is an easy procedure. We're replacing a complicated procedure for an easy procedure. But the easy procedure is only good when we're, whatever this means, close to point A. So close to -4 in this example. A new little idea, that of a differential. Let y equal f of x be a differentiable function. The differential dx is an independent variable. The differential dy is defined as dy equals f prime of x dx. All right. This is probably one of my least favorite parts of Calculus 1. I don't want to treat these differentials as if I was doing division, and then we would divide both sides by dx and get dy dx equals f prime of x. And I've made such a big deal about dy over dx not being a quotient. That's not division. It's a limit of a quotient. It represents something else. And then here they introduce this stuff. We're going to use these differentials in very specific settings. This section here, and on down the road in chapter 5 when we do something called U substitution. Other than that, we'll largely leave differentials alone. But there's what the definition of dy is in terms of dx. So computing them is easy. Computing them as easy as it is to differentiate. and you're good at differentiation. So let's look at y equals secant x squared minus 1 and find dy from that. All you got to do is differentiate and stick a dx on the end. If f of x equals secant x squared minus 1, we've got by the chain rule then that dy being f prime of x, well, a little typo there, should be dx, f prime of x dx. We differentiate the secant of x squared minus 1. That's a composition, so we'll need the chain rule. See? Derivative of secant is secant tangent. Secant tangent of what? The stuff inside, x squared minus 1. So we pick that up inside both of those as always. And then the chain rule says you have to multiply by the derivative of x squared minus 1, which is 2x. And since you're computing a differential, I got to write this down, we put a dx on the end. So dy is, I guess I can write the 2x out front, 2x secant x squared minus 1 tangent x squared minus 1 times dx. So we're about to use them for something, but for now, computations of differentials, piece of cake. You take derivatives and then you put a dx at the end. Let's do another one, but this time with some inverse trig functions and exponentials. Really just mostly for practice of taking derivatives of these compositions. Ooh, compositions, derivatives, that'll require the chain rule. How many layers of functions do you have here? There's, let's see, there's a first one, x squared plus 1. It's inside a square root function. There's a second one. It's inside a tangent inverse function, and that's inside an exponential function. 4 layers of functions that'll require 3 applications of the chain rule. It's 1 less than the number of levels of functions. Okay, so chain rule tells us how to differentiate. We'll take a derivative and then stick a dx on the end. There's that dy again, stick a dx on the end, cut and paste. All right, so differentiate the exponential. We just rewrite it. Leave the inner stuff alone. We did differentiate, just nothing happens when you differentiate the exponential base e. So derivative of e to the whatever power, rewrite the power, the inner function, multiply by the derivative of the inner function, chain rule. In that composition, the first function we encounter is the tangent inverse. How do you differentiate tangent inverse of something? 1 over 1 plus the something squared. The something is the square root of x squared plus 1. So we'll get that in there, inside there, then being squared, times the derivative of the stuff inside that tangent inverse function, which is, if you like, x squared plus 1 to the 1/2 power. Take the square root and think of it as a 1/2 power. Then we bring the 1/2 down, rewrite the inner stuff, subtract 1 from the exponent, getting a negative 1/2, multiply by the derivative of the stuff inside. Hey, we use the chain rule 1, 2, 3 times, easy enough to see, because I got the little arrows. And I predicted that because we had 4 layers of functions. It's 3 applications of the chain rule. And then stick a dx on the end because it's a differential. Clean it up a little bit, I guess. So the 2 and the 1/2 cancel. And that's, let's see, the squaring and the square root. We can get rid of the radical there. We'd have 1 over 1 plus x squared plus 1. That's 1 over x squared plus 2. So that simplifies a little bit. The x squared plus 1 to the negative 1/2, put it in the denominator as a square root. We still got this thing out front over here. Don't forget the dx because it's a differential. And we got the x left over. So anyhow, it simplifies down to this. We're not going to do anything with it, so whatever. But we will use differentials to do some approximations here soon. Okay. So let f of x be differentiable at x equals a. The approximate change, the differential estimate of change, in the value of f when x changes from a to a plus dx is the change delta L in the linearization of f at a. All that information is really contained in the little picture, and we'll have equations for it. Let me make that little picture not so little. So what they're saying is, here's a function in blue. At point A, we've got a linearization. there'll be something special about point A. It's easy to find a function f at point A. For example, if it was a trig function, it'd be easy to evaluate its special angles, but not all angles. Then we're going to move away from A a little bit, denote that little bit by dx. We'll also denote it by delta x, and then use those two interchangeably. So move over a little bit. It's not so little in the picture. Well, you want to be able to see it. Then, how much does the function change? If x changes by a little bit, I expect y to change by a little bit. That's continuity. But we're estimating the change in y, denoted with a delta y. So that's how much the function changes when x moves from a to a plus dx, or a plus delta x. The function changes by this much, denoted with a delta y. The linearization, delta L, changes by this much. It's just a rise over, slope is rise over run. It's a rise over run thing. And we get delta L changes by the amount f prime of a dx. So what we're saying is delta L f prime of a dx, we're denoting it also as df. That's an approximation of the change in the function f when we move the input value from a to a plus dx. So I expected the line to approximate the function. So I expect the changes in the line to approximate changes in the function. And they're not going to be precise unless the function itself is a line. So this is the type of approximation we're actually going to use to do some examples. Here's a little more formulas, and here's the example we'll do. If we know the value of a differentiable function f at a point A, so A is a nice point, I know how to evaluate function f at point A, like a trig function at a special angle. So that's the starting point. And we want to estimate the value of f when x changes a little bit from a to a plus delta x, or a plus dx. We'll take delta x and dx interchangeable. We're not doing that with the y's. The y's get approximated. Then we have f of a plus delta x. That would be f of a plus dx, because we're using those symbols interchangeably. And that would be f of a plus the change in y, the actual change in y. We're approximating that change in y with the differential dy. The differential dy, or df, calculated here. And so the equation we get is the value of the function at the new x value is approximately the value at the old x value, the good value a, plus this little bit of change. We're approximating change in the function with change in the linearization. This is the change in the linearization. We got a formula for it right here. So, long story short, we're using derivatives to approximate changes in functions. Derivatives were slopes of tangent lines. If the function itself happens to be a line, these won't be approximations. These will be precise. If the function happens to be curvy, these won't be precise. And we'll have to stay close to a. That is, this delta x thing will have to be little, whatever little means. If the function's really wiggly, then these are maybe not such good approximations. It depends on how much the original function wiggles. If we're approximating it with a straight line and it wiggles a lot, it's not going to be a very good approximation. Well, bulk of the functions you've dealt with in the past are really not that wiggly. Let's use a sine function. Use differentials to estimate the value of the sine of 31 degrees. Okay, first off, degrees won't do. We'll have to do our thing in terms of radians. Secondly, hey, 31 degrees is close to a special angle. You know what the sine of 30 degrees is, because 30 degrees is a special angle. So we'll use the value of the sine function at 30 degrees. Sine of 30 degrees, that's a half, isn't it? Sorry, pi 6 radians, it's a half. So sine of 31 degrees is it's close to a half. we just want to estimate the difference, the change in the function sine when we vary the input from 30 degrees to 31 degrees, doing our computations in terms of radians. And that'll give us an estimate, and it turns out to be a shockingly good estimate given how crude this approach is. All right, first, 31 degrees is 30 degrees plus 1 degree. That's pi 6 radians, plus 1 degree is pi over 180. Radians, if you keep up with the units, it's unitless. So I'll put it in parentheses there on the side. And we're taking the function to be the sine function. F of x is sine x, so that f prime of x is cosine x. Derivative of sine is cosine. We'll take a to be pi 6, and we'll take delta x or dx to be that 1 degree, that pi over 180. Then I've repeated the formulas here so I don't have to bounce back and forth. The sine of 31 degrees, well, that's the same in terms of radians as the sine of pi 6 plus pi over 180. That is the f of a plus delta x. That is the f of a plus the change in the function. Delta y was the change in the function. We're approximating the change in the function with the differential dy, which is computed like this. So there's where the approximation comes in, when we change from delta y to approximating it with dy. So we're changing from actual function values to things related to the linearization, the approximation to the function with L of x. All right, dy is f prime of a dx when it's evaluated at x equals a, and that's what we're doing. So we need f of a, that'd be the sine of pi over 6, and I know what that is. That was the point. I know how to evaluate this function at 30 degrees. So I know how to roughly evaluate it at 31 degrees. Let's see how rough the approximation is too. To that, we need to add f prime of a. That would be cosine of pi 6 times dx. Dx was 1 degree, well, pi over 180, because I have to use radians. And there's what we get. And I know the sine of pi 6, and I know the cosine of pi 6 because it's special angles. So we're using special angles, nice values for the function we started with, the sine function, where I know precisely how to evaluate that function at those values. And then we're approximating nearby. Sine of pi 6 is a half. Cosine of pi 6 is square root of 3 over 2. That produces this thing here, which I can simplify a wee little bit to write like this, which really doesn't mean anything to you if we're actually doing approximations. This itself is approximation. Remember, we get the approximately equal to right there. If I feed that to the calculator and take, what I got, like 6 decimal places, we get something like this. Yeah, the sine of 30 degrees is 1/2, is 0.5. And this is a little bit more than 0.5. If I ask my calculator to give me the sine of 31 degrees, it gives this out. So we got pretty close. This is 0.5150. This is 0.5151. So to 3 decimal places, this is accurate. And this is a really fairly crude way to approximate functions, as you'll see in calculus too, when you have more sophisticated ways to approximate. But not too bad. We got to, what, 1 part in 5,000 just with this little technique here. So we're correct to 3 decimal places, not to 4. It's actually off in the 4th decimal place. So there's a way to approximate functions, and there's a type of application you might have for this kind of thing. Back to the notes. Let's see, we want to do number 44 and then talk about percentage change. Number 44 is a similar type thing. Consider f of x equals x cubed minus 2x plus 3. Take x sub 0 to be 2 and dx to be 0.1. Find the change, delta f. F of x sub 0 plus dx minus f of x sub 0. The value of the estimate df equals f prime of x sub 0 dx, and the approximation error. how much did the function actually change versus how much we approximated the change. Okay, this is question 44 out of the section. They've replaced the a with an x of 0 for reasons known only to them. Also, the spirit of why you would do the approximations doesn't really hold here, because you can cube numbers and you can do this arithmetic. I give you an x value, you can compute this stuff here precisely. That really the spirit of this is to use complicated functions. Well, to illustrate linearization, let's go through this. Certainly linear functions are even easier to plug numbers into than this function is here, but you can't do it even for this one. So for the sake of illustration, we work this one, starting out with, they gave us the function, so we'll need the derivative. We'll need the derivative when we calculate the differential stuff over here. So f prime is 3x squared minus 2. All right, they want to know the actual change in the function. Okay, since it's a reasonable function, we can actually do that. So that's one reason to give us a reasonable function. Delta f is the change in the function as the input value moves from x of 0 to x of 0 plus dx, definition of delta f. It's in the notes. X of 0 is 2, dx is 0.1. Okay, so we'll plug that in. Maybe rewrite that a little bit. We're dealing with f of 2.1 minus f of 2. Yeah, because x changed from 2 to 2.1. Remember, dx was 0.1. And these we can plug into the original function, and these we can actually evaluate. You could do this without a calculator. It's kind of the idea. You could do this by hand. I wouldn't want particularly to cube 2.1, but I certainly can. And when we do the arithmetic, we get 8.061 minus 7. So the function changed by an amount 1.061. All right, that's the actual change. What's the estimated change? What's the differential df? Well, df is f prime of x sub 0 dx. X sub 0 is 2. Dx is 0.1. F prime of 2 would be 3 times 2 squared minus 2. There's f prime from upstairs. So there's f prime of 2. Dx is 0.1. I do the arithmetic and we get 1. So the actual change was 1.061. The estimated change was 1. So not bad. It's like a 6% error-ish. So if we'll take the absolute value of how much it actually changed minus how much we estimated the change, that value is 0.061. Is that good? Is that a little number? Well, it kind of depends on the magnitudes of what you're estimating. If I'm measuring things with a level of accuracy of, say, 0.061 kilometers, so that's what? It's like 60 meters. 60 meters, a good approximate, a good error to make. Well, if I'm estimating the distance to the sun, 60 meters is pretty good. If I'm estimating the length of my driveway, if I'm getting it repaved, 60 meters ain't good at all. So it depends on what you're estimating. When I look at the raw numbers, I bring this up because the next thing we look at is going to talk percentage error. But there's the numbers we reproduce. Is this good? You know, comparing these, it looks pretty good. Here, this represents about 6% of that. So it's about a 6% error. If I talk in terms of percentage errors, hey, let's talk in terms of percentage errors. So there's illustrations of the computations. One more idea is, how good are these approximations? Say in terms of a percentage error. We can compare actual changes in a function and the estimated change, which is calculated from the differentials, as follows. We can measure straight up the absolute change. That's just a change in function values. We're estimating that change with differentials, as we just saw. The relative change is the change in the function divided by the value of the function at a. Our estimate of the relative change is the differential divided by the value of the function at a. Multiply those by 100%, and that gives a percentage change. So we have these true changes and these estimated changes. And as foreshadowed, I'm really interested in probably more the percentage change than I am the absolute change. It tells you how accurate the measurements you're making are. So this is really totally applied stuff, applicable stuff. Let's look at a couple of examples that illustrate this percent error. And actually the computations aren't too hard. It says, number 56, the edge of a cube is measured with an error of at most 0.5%, half a percent. What is the maximum corresponding percentage error in computing the cubes? Part A, surface area. Part B, volume. Okay, so it's all about percentage error. They talk about an error in terms of percent of the measurement of the length of an edge of a cube. They want to know the percentage error in the corresponding measurements of the surface area of that cube and the volume of that cube. Okay, so surface area of a cube of edge x. So each face has x squared, square units, whatever the units are. X squared is the area of each edge. Cube has 6 edges, 6 faces. So its area is 6x squared. The volume of a cube with an edge of size x, volume is just x times x times x, x cubed. The edge is measured with an error of at most 0.5%. So the percentage change in the edge is dx over x times 100. Different fonts here. This software generated these fonts. That's a times symbol, and these are x's, right? So I know they look similar, but we took the estimated change divided by the magnitude and then multiplied by 100%. That's the thing that we called our estimate of the percentage change, and we're told that's less than measured with an error at most 0.5%. So we get this less than or equal to 0.5%. Let's get the percentages in that multiplication symbol out of the way. Divide out by 100% and then multiply the x on the other side. You'll get dx is less than or equal to 0.005x. I expect decimal approximations in a lot of this numerical stuff. But that gives us an upper bound on dx in terms of x, and that's what we're given. They want to find the maximum corresponding percentage error in surface area. All right, here's surface area. We'll do the same kind of thing. We'll take a differential of surface area divided by surface area, just like we did with the differential of the length of a side divided by the measured length of a side. So we need, from A, we need dA. A is a function of x, 6x squared. So dA is the derivative, 12x, times the differential dx. The percentage change in area then is dA divided by A times 100%. Take the approximate change divided by the size of the function, multiply by 100% to make it a percentage. Okay, so we substitute in dA is 12x dx. A is 6x squared. Multiply that by 100%. We had a bound on dx up here. Dx is less than or equal to 0.005x. So let's use the inequality, replace the dx with this quantity. All right. And look at this. We got x squares in the numerator and we got x squares in the denominator. So this is going to simplify. The x squares all cancel out. You crunch the numbers and get the percentage out of the way, and crunch through that, you get 1%. So we're getting a 0.5% error in measuring the length of a side corresponds to up to a 1% error in measurements of the surface area of that cube. It doubled. Why did it double? You see where the 2 came in? Right there. I bet it's got something to do with that x squared. We were measuring an x thing, and here we're talking about an x squared thing, if I may be so informal. I bet you that 2 there has something to do with the fact that we doubled here. Let's check on volume, because that involves a cube thing. If it tripled, then maybe I'm onto something here, in this special case at least. Volume was x cubed, so the differential of volume is to differentiate 3x squared dx. It's a differential, don't forget the dx. So the percentage change in volume is dv over v times 100%. dv is 3x squared dx. V, volume, is x cubed times 100%. We've got a bound on dx of 0.005x. Plug that in, it gives us an inequality, and they ask us maximum. They ask us for an upper bound in their question. They had to, because that's the kind of information they gave us. So substitute for dx, that upper bound on dx is given upstairs. We've got, hey, look, we got an x squared and an x. That's an x cubed in the numerator and an x cubed in the denominator. Those cancel again. Crunch through the numbers and you get 1.5%. Hey, that's 3 times what we initially had. Yeah, I bet that's not a coincidence. We had something related to squaring in part A, and we doubled. Something related to cubing in part B, and we got a tripling in the percent error. That's not a coincidence. Now, if it was a more complicated function, I'm not sure exactly what would happen. But since we simply had a squaring function times a constant and a cubing function here, that's what led to these particular answers. So there's how we can find percentage error estimates of other things like areas and volumes based on a single percentage area of the measurement of an edge. Okay, this is a similar type question, really. They consider a cylindrical storage tank. Question is, about how accurately must the interior diameter of a 10-meter high cylindrical storage tank be measured to calculate the tank's volume to within 1% of its true value? All right, so you got a giant cylindrical tank. You're going to measure the interior diameter and use that to approximate the volume. You take a ruler, you try to measure something, there's going to be little uncertainties in the measurement is the idea. We want to estimate the tank's volume to within 1% of its true value, and that's going to require a certain level of accuracy, how accurately, in terms of our measurement of the diameter. Part B, about how accurately must the tank's exterior diameter be measured to calculate the amount of paint it'll take to paint the side of the tank to within 5% of the true amount. So in the first one, we want to measure the volume within a 1% error. And in the second one, they talk about paint. It's the surface area that matters. We want to measure the surface area to within 5%. So when they talk about these percent things, this will be a differential over an exact value times 100%, as always. The volume of a cylinder of diameter, D equals 2R. They ask us about diameter. You're used to probably computing volumes and surface areas of cylinders using the radius. So let's take care of that. Diameter is 2R and height is H. Volume is pi r squared H for a cylinder. Okay, so we'll replace the R with a D. We'll get R as D divided by 2. So we get a D over 2 there because I want to do things in terms of this diameter. Also, they told us the height of the tank. 10 meters high. Okay, so the height is 10, so we don't have to worry about errors and measurements of the height. We know the height precisely somehow or other. So we'll plug 10 meters in there. It's a volume. It'll be meters cubed, by the way. And simplifying, we get, let's see, pi d squared over 4 times 10. Can take the 10, oops, the 10 and the 10 and the 10 divided by 4 and write it as 5 halves. So we simplify it a little bit. The differential of volume, Okay, differential of volume would be differentiate with respect to D, and then put a dd on the end. It's a differential. Differential of volume would be 5 pi over 2, bring the 2 down. So we get a 2d dd, the differential. So capital D's for diameters, little d's for differentials. But there's what we get for the differential. I can cancel the 2's and simplify it to 5 pi d dd, meters cubed, by the way. So there's volume and a differential of volume. Let's do the same thing for surface area. The surface area of the side of the cylinder of diameter 2r and height h is 2 pi rh. We stated that in the previous section, the surface area for a cylinder. It'd be the circumference times the height. That should be plausible. We're measuring the walls, not the top and the bottom of the thing. So the circumference is 2 pi r for a circle of radius r, and then times the height, and that'll produce a surface area. Imagine taking the cylinder, cutting it open and peeling it out. You'd have the height, and then you'd have the circumference as dimensions of a rectangle. But 2 pi rh is what we're interested in. We need to do this in terms of the numbers we have. That would be r equals capital D over 2. So replace the r with a capital D over 2. They told us the height is 10 meters, so put a 10 there. Simplify and calculate a differential. So dA is 10 pi dd, square meters since it's area. So we've got volume, differential of volume, area, differential of area. And they've asked us about percentage estimates. Okay, for the volume, we'll take dV divided by V, multiplied by 100%. Area, we'll take dA divided by A, multiplied by 100%. All right. We want dV over V times 100%, say, to equal 1%. Let me go back and read the question from part A. About how accurately must the interior diameter, capital D, of a 10-meter high cylindrical storage tank be measured to calculate the tank's volume, V, to within 1% of its true value. So we want the percentage error to be, say, 1%. We want dV divided by V times 100% to equal 1%. Well, we had formulas for dV and V from the previous slide. Here's those two formulas. We got a d in the numerator and a d squared in the denominator. So not everything cancels this time. I can cancel the 5 pi's. Take that 2, maybe put it in the numerator. So we're left with 2 dd over d. Hey, dd over d times 100%, forget the 2 for a second, that's a percentage error in the measurement of the diameter d, and that's what they were asking us about. So here's the thing we were looking for. dd divided by d times 100%. That's the thing we're looking for. Here's an equation involving it. The 2's in the way. Well, divide it out. So divide both sides of this by 2 to get dd divided by d times 100% equals 0.5%. That's how accurately we need to measure diameter d, within 0.5%, say 0.5%. How about surface area? Well, we'll do the same thing, and a similar thing will happen. We'll end up with a dd over d times 100% in the surface area as well. Let's go back and read the question for part B. Previous slide. About how accurately must the tank's exterior diameter, also calling it d, be measured to calculate the surface area of the tank to within 5% of the true amount. They talk about paint, they're really talking about surface area. We've got that surface area here, and here's a differential. So we'll take this divided by that times 100%. We want that to be equal to, say, 5%. Okay, so we want the differential of surface area, I've called it S for surface here, should still probably call it A. The differential of surface area divided by surface area times 100%, we want that to equal 5%. We had formulas for those. Differential of surface area was 10 pi dd. Surface area itself was 10 pi d. The 10 pi's cancel, we get dd over d times 100%. We want that to equal 5%. So dd over d times 100% itself must be 5%. There's no balancing to do, like we had to divide by the 2 up here. The answer just came out of that one. That one's actually super simple, computationally at least. So part 2, we need to measure for this one, for that level of accuracy, we need a 5% accuracy. So there's some applications of approximation, some idea of this percentage error and estimated percentage error. So this is useful stuff you might see in future. I guess it could potentially come up in a physics class. Could potentially come up in an applied math class where you do estimations. All right, to wrap this section up, we want to prove the chain rule. To do so, we need a preliminary lemma. Some good news, this is almost computational. It's got some epsilon symbols in it, but we're going to be less hands-on about the epsilons. We're talking derivatives, back to the chain rule, so we'll ultimately deal with limits for this. And the epsilon delta stuff, we won't be very hands-on with it, though it's there. Lemma 3.11a says, if y equals f of x is differentiable at x equals a, and x changes from a to a plus delta x, the corresponding change, delta y, in f is given by delta y equals f prime of a plus epsilon delta x, in which epsilon approaches 0 as delta x approaches 0. So we're looking at a change in the function, an exact, not differential stuff. This is in this section because there's ideas that are related to the differential stuff. But we're going to take the actual change in the function and write it like this, is the first claim. Secondly, whatever it is we choose for epsilon, that's going to approach 0 as delta x approaches 0. Secondly, the chain rule. So to the supplements, prove that. Okay. The approximate error, and we don't want an approximate error, we want an actual change in, but the approximate error, delta f minus df at x equals a is delta f, change in the function minus our estimation of that change. We're estimating the change using differentials. We'll get rid of the differentials. They're just passing through on this computation. So change in the function minus the estimation of the change. We're taking dx equal to delta x, so the differentials are gone now. So little delta f is some change in the function. It's actually numbers. Little delta x is some numbers. Little delta x won't be 0. We actually had change from x equals a to something different. I need a little wiggle room there. We can take this change in the function, rewrite that as what it is by definition. Delta f is the function evaluated at a plus delta x minus f of a. It's how much the function changed when the input changed from x equals a to x equals this, a plus a little bit, a plus delta x. And for that matter, delta x could be negative. So there's the change in the function. We're subtracting f prime delta x. This can be rewritten like this. Take the delta x and distribute it and see if it actually corresponds to this. Delta x times f prime of a, right. Delta x times this thing here, well, the delta x's will cancel. You'll be left with this numerator, which is what we have here. So indeed, those are equal. And we're going to call that epsilon delta x and let epsilon be this stuff in the parentheses. All right. So we've got the approximate error written in terms of this. So if we look at the extra claim, epsilon approaches 0 as delta x approaches 0. We want to show this thing here approaches 0 as delta x approaches 0. Hey, does that look familiar? That's a difference quotient for function f at x equals a. Going back to our definition of derivative at the very beginning of chapter 3. That's a difference quotient. So if we take a limit as delta x approaches 0, this is going to approach the derivative of f at a. This is going to approach f prime of a. And this whole thing is going to approach 0 because this is f prime of a. Subtract it off. F prime of a exists, doesn't it? Yeah, we hypothesized differentiable at x equals a. F prime of a exists, so as delta x approaches 0, the difference quotient approaches f prime of a by the definition of derivative. So the epsilon quantity approaches 0. So as delta x approaches 0, the epsilon quantity approaches 0. That's the second part. The other part was delta y can be written in this form here, and that's exactly what we have upstairs. We have delta y, say, is delta f of x. We have that written in terms of f prime of a plus epsilon delta x. Here's the epsilon plus delta x stuff. The df part, take it to the other side of the equation. df is f prime of a delta x. Say that, it doesn't say that explicitly on this slide anywhere, but that's how we computed the df. So from equation star up there, we get the equality claimed here. All right, it's a technical lemma. We need that to establish the chain rule. And it's based really on nothing but the definition of derivative, it turns out. This differential stuff that I always get a little unhappy about. I don't like approximating stuff. It was just around temporarily. We ultimately did computations with the deltas. And we ultimately did precise computations. Okay, so chain rule says composition of functions, remember, we wrote them like this. F of u is a differentiable function at point u equals g of x, where g of x itself is differentiable at value x. Then the composition, almost there, the composition f composed with g of x, that is, f of g of x, is differentiable at x, and the derivative of the composition is what you're used to by now. Differentiate the outer function, rewrite the inner function, and then multiply by the derivative of the inner function. So we're proving that, and we're going to use that lemma that we just had. First, let x sub 0 be a point at which g is differentiable, and suppose f is differentiable at g of x sub 0. So we've picked a particular point at which the hypotheses are satisfied, and then we're going to show the derivative evaluated at x sub 0 is f prime g of x sub 0, g prime of x sub 0. It's of this form. Since x sub 0 is an arbitrary point satisfying the hypotheses, this will hold for all x. But first, we've picked a particular point. It's okay, it's an arbitrary point. The satisfying the hypotheses. All right, so we can use the lemma, let delta x be an increment of x, and delta u a corresponding change in u. U equals g of x. Well, g is change in g when x changes by an amount delta x, say would be g of x sub 0 minus g of x sub 0 plus delta x. So we've modified the input by an amount delta x. That generates a change in the g function. We're using this intermediate value u, or intermediate variable, to represent g. And we get delta u, or delta g, is represented by this. It's the change in the g function. And the corresponding change in the f function, delta y, is represented by f of u sub 0 minus f of u sub 0 plus delta u. So as delta x changes, that induces a change in the g function and hence a change in the f function. And they cascade through this middle variable u. We've got kind of an outer function and an inner function. And that inner function is represented with u equals g of x. There you go. By lemma 3.11.a, we have the change in u can be written in the form g prime of x sub 0 delta x plus epsilon 1 delta x. That's exactly what we had from lemma 3.11.a, except applied to the g function instead of an f function. We can factor that delta x out if you like. And we had from the lemma that epsilon 1 approaches 0 as delta x approaches 0. So there's change in u written in terms of this. How about we look at the change in f and apply the lemma to that as well? Change in f, delta y, y equals f, that's how we'd represented it, just as we had u equals g, would be the derivative at u sub 0, delta u plus epsilon 2 delta u. That's the form we had from the lemma. We can factor the delta u out if you like. And we've got epsilon 2 approaching 0 as delta u approaches 0, also from the lemma. So getting lots of mileage out of that lemma, approximating changes in functions divided by changes in variables is what we'll do ultimately. And then take limits, and those changes will become derivatives. G is differentiable at x sub 0, hypothesis. So G is continuous at x sub 0. Continuous functions are differentiable, theorem 3.1. So the limit as delta x approaches 0 of delta u, remember delta u is defined as this, will be 0. Limit as delta x approaches 0, g of x sub 0 minus g of x sub 0 plus delta x. If it's continuous, I can substitute in delta x equals 0. Continuity means you can evaluate limits by substitution. Substitute in delta x equals 0. We're left, of course, with g of x sub 0 minus itself. So we get a 0 out there. So we do have delta x approaching 0, implying delta u approaches 0. Delta u approaches 0 as delta x approaches 0. So delta y, we had written like this as above. Delta u, we had delta u written from the previous slide in this form here. So delta y equals this stuff involving the f prime function and the epsilon 2. Delta u involves a g prime function and the epsilon 1, and there was a delta x tacked on to the end there. So substituting in for delta u from the previous slide. Now we can divide. I'm looking for difference quotients. Delta y divided by delta x. So we've got that difference quotient. This will lead to the dy dx when we take a limit. On the right-hand side, if we'll FOIL out what we have written here, excuse me, we'll have f prime of u sub 0, g prime of x sub 0, epsilon 2 times g prime of x sub 0, epsilon 1 times f prime of u sub 0, and epsilon 1 times epsilon 2. So FOIL this, divide by the delta x, produces that. And we know as delta x approaches 0, epsilon 1 and epsilon 2 both approach 0 by that lemma. We're almost there. You like the looks of this, f prime of u sub 0, g prime of x sub 0? You ought to, if you'll think what u sub 0 is. U sub 0 is g of x sub 0. This is the thing we're looking for. All this stuff's going to go away on the next slide when we take a limit. Okay. As delta x approaches 0, both epsilon 1 and epsilon 2 approach 0, reiterating that, copying from the previous slide. We do know that g prime of x sub 0 and f prime of u sub 0, they're just some fixed numbers. That's why we fixed x as x sub 0 in the beginning. And then we get the derivative of y with respect to x evaluated at x sub 0 as a limit as delta x approaches 0 of that difference quotient. We've got the x sub 0 stuck in there. So it's a derivative at a single point. Take a limit as delta x approaches 0. This is what we had for delta y divided by delta x on the previous slide. And we keep this part. We get a 0 in the limit from the epsilon 2, a 0 from the epsilon 1, and 2 zeros over here, epsilon 1, epsilon 2. All that stuff is 0. We're left with f prime of u sub 0, g prime of x sub 0. Hey, u sub 0, I pointed out on the previous slide, I don't see it on this slide, was g of x sub 0. And we've shown the derivative of y with respect to x evaluated at x sub 0 is f prime of g of x sub 0, g prime of x sub 0. Take that x sub 0, being an arbitrary point satisfying the hypotheses, replace it with x itself, and we get dy dx, no evaluation, is f prime of g of x, g prime of x, and that's a chain rule. So there's a proof for the chain rule. It's in this section because they use some of the differential ideas and the approximation stuff, but it is still largely just using the definition of limit. I'm sorry, definition of derivative in terms of limits. We took a limit as h approaches 0. We used delta x's instead of h, but it ultimately went back to the limit. And now we have, I think we've proved everything we need to prove about differentiation. You know all the properties, and we've gone through proofs of all of those properties. You're good to go on differentiation. Chapter 4 is applications of differentiation. So we're well over halfway through the material. Chapter 4 will apply derivatives to functions, mostly to graph them. We'll do some optimization stuff as well. And in chapter 5, we'll do something a little bit new, anti-differentiation, differentiation backwards. And the kinds of problems we'll address will totally shift gears. The techniques will be somewhat similar to what we're doing here, though. But you're good to go on differentiation. You know as much as anybody knows about differentiation at this stage. So have a nice day. I will see you soon, and we'll get to working on chapter 4.